Hello friends, a very good morning to all the students. Am I audible to all? Okay, fine. Thank you all for your responses. So dear students, if you remember in the last lecture, we have discussed the numericals of the Otto cycle. And remember friends, the numericals of the Otto cycle are very important. They can be asked in your theoretical examination, and each numerical can be of the weightage of 7 marks. So friends, we are discussing the chapter that is the heat engines. Let me ask you, in my yesterday's lecture, I had given one of the numerical as the practice numerical. How many students has calculated that practice numerical which was given in the last lecture? Any student has calculated the practice numerical? This was the numerical which was asked to do by yourself. It was a very easy numerical related to the Otto cycle. Any student has done this numerical? Okay, fine, no issue. So just I am explaining this numerical once again, and I will be displaying the answers of this numerical so that you can note down the answers and then try to solve these numericals and get the answers, match the answers which I am showing. So friends, if you understand the numerical in the Otto cycle, first we are given the Otto cycle. The air at the beginning of the isentropic compression is at 1 bar and 15 degrees Celsius. So we are given the pressure P1 that is 1 bar and temperature T1 that is 15 degrees Celsius. The ratio of compression that is small r is equal to 8. The heat added during the constant volume process is 1000 kilojoule per kg. So that is Qs is equal to 1000 kilojoule per kg, converting that value into joule per kg. In the next step, to find in this numerical, we need to calculate the maximum temperature in the cycle. So if we understand the TS diagram, the maximum temperature in the cycle is achieved at point 3. So we need to find T3. Then we need to find the air standard efficiency of the Otto cycle, that is eta Otto. And finally, we need to calculate the work done per kg of air, that is W. So doing the same procedure in the calculations, I am just giving you the answers. So whenever you are calculating this numerical by yourself, you can check the answers, you can correlate your answers with mine answer. So on calculations, the first answer which is obtained, that is the maximum temperature attained in the cycle T3, that is 2055.37 Kelvin. So this is the maximum temperature answer we are getting after doing the calculations. The second answer, that is the air standard efficiency of the Otto cycle, that is eta Otto, comes out to be 56%. And friends, remember, the efficiency must always be presented in percentage, and it should be presented in the round figures. Do not write the efficiency answer in terms of points, in terms of the decimals. Just make the answers in the round figure. And the final answer, that is the work done per kg of the air, that is W net is equal to 560 kilojoule per kg of air. So these are the three answers of this practice numerical. Dear friends, whenever you are solving this numerical, if you are not getting this answer, if you are stuck somewhere, then you are free to ask me about your doubts. I hope the answers and the numerical is clear to all the students. Have you written all these answers in your notebook and the numerical? I want your responses in the chat box. Okay, fine. So now let us proceed further with the next topic related to the heat engines. The next topic, that is the diesel cycle. And friends, remember, the diesel cycle is also one of the most important questions which is asked from this chapter. So in this lecture, we are going to understand some of the basic concepts related to the diesel cycle. Then we will be understanding the different processes in the diesel cycle. And finally, we are going to make the derivation for the efficiency of the diesel cycle. So let us start with the discussion of the diesel cycle. Dr. Rudolf Diesel, a German engineer, first successfully developed this particular cycle. And since it was developed by Dr. Rudolf Diesel, this cycle is known as the diesel cycle. Remember friends, the another name of the diesel cycle, that is the constant pressure cycle. Because in this cycle, the heat is supplied at the constant pressure conditions. Let me ask you a question. What was the another name of the Otto cycle? What was the another name of the Otto cycle which we have studied initially? Very good, getting the responses from the students in the chat box. The perfect answer I am getting. So the another name of the Otto cycle, that is the constant volume cycle. Because in the Otto cycle we have understood that the heat addition takes place at constant volume conditions. But remember friends, now in the diesel cycle, the heat addition will be taking place at constant pressure conditions. And this is the most important difference between the diesel cycle and the Otto cycle. And since in the diesel cycle, the heat is added at constant pressure conditions, this cycle is known as the constant pressure cycle. So the diesel cycle is an ideal thermodynamic cycle that describes the function of a compression ignition engine. Compression ignition engine that represents the diesel engine. And friends, if we have understood the concepts about the working of the automobiles, the engines of the automobiles, we have understood that the petrol engines are different and the diesel engines are different. Okay, we will be understanding all these concepts in more details, in more practical sense when I am discussing the interesting chapter, that is the internal combustion engines. At that chapter, at that point, I will be discussing several important concepts related to our petrol engines as well as the diesel engines. But at this point of the time, you just remember that the diesel engines, they work on the diesel cycle. So let us proceed further with the discussion of the diesel cycle. So these are the different processes of the diesel cycle. 90% of these processes are same as that of the Otto cycle. Only the change comes, that is in the process 2 to 3. In the Otto cycle, we have understood the process 2 to 3, heat addition is taking place at constant volume conditions, but in the diesel cycle, this heat addition will be taking place at the constant pressure conditions. Rest all other things, they remain similar as the Otto cycle. The processes are similar, the working will be similar, all other concepts will be similar. Only the difference will be in the Otto cycle, the heat addition takes place at constant volume conditions, but in the diesel cycle, the heat addition takes place at constant pressure conditions. This is one of the most important point to be remembered in context of the Otto cycle and the diesel cycle. I hope you are understanding the concepts, all the students. I want your comments in the chat box if you are understanding the points. Okay, fine. So friends, in the diesel cycle, the same process is as that of the Otto cycle 1 to 2. That is considered as the isentropic compression or the reversible adiabatic compression process. 2 to 3, that is the change which is coming in the diesel cycle. 2 to 3 process, that is the constant pressure heat addition process. 3 to 4, that is again the isentropic expansion or the reversible adiabatic expansion process. And finally 4 to 1, that is the constant volume heat rejection process. In this figure also you can just mention from this 0 point to the volume V2, that is considered as the clearance volume Vc, and starting from V2 to V1, this entire range, entire volume area, that is considered as the stroke volume or the swept volume. And one of the important friends, remember that in 2 to 3 process, whenever we are supplying the heat or supplying the diesel fuel in the practical diesel engines, we will be using the injectors. And in the injectors, we will be spraying the diesel, because to undergo the injection process, one another ratio will be coming into the picture, that is the cut-off ratio. This cut-off is very essential in the diesel engines in order to have the injection of the diesel fuel. So friends, I am repeating this important point once again. In the constant pressure process 2 to 3, we will be supplying the diesel fuel with the help of the injector. And for injecting the diesel fuel into the engine cylinder in the fine atomized spray, now a new ratio will be coming into picture, that is the cut-off ratio. The cut-off ratio, simply understand that it is the cut in the pressure conditions. When the pressure of the injector is cut, the spray is stopped, and when the pressure is again released, the cut-off is released, again the injector is spraying the fuel. I hope this concept of cut-off ratio is clear in your minds. Remember friends, the cut-off takes place only in the process that is 2 to 3. When we are supplying the energy into the engine cylinder, the cutoff takes place, that is process 223. Is it clear to all the students? The cutoff ratio, a new term we will be using in the derivation of the efficiency. Okay, fine. So now let us proceed further with the most and the most important question related to the diesel cycle, that is the derivation of the efficiency of the diesel cycle. So I just advise all the students that you also start noting down the equations of the efficiency so that the derivation is perfectly clear in your minds and you are understanding the steps of the derivation. So in making the efficiency of the diesel cycle, the derivation, we need to understand the PV diagram as well as the TS diagram. We will be using the reference of both these diagrams. So the first step of the derivation, we are considering the unit mass of the air undergoing a cyclic change during the diesel cycle. Similar to the Otto cycle, in this cycle also, Rudolf Diesel has considered the mass, that is 1 unit. Now the amount of heat supplied during the constant pressure process, that is process 223, is given as Q in is equal to Cp T3 minus T2. And now the amount of heat rejected during the constant volume process, that is process 421, is Q out, that is Cv T4 minus T1. Is it clear to all the students? Remember friends, in the Otto cycle, this was a constant volume, so we have written Cv. But in diesel cycle, the heat is supplied at constant pressure, so we have written Cp. That is only the change in the diesel cycle. Have you understood all up till this point? All the students? Have you understood up till these equations? Okay, fine. So let us proceed further. Now the net work done, that is W net, is equal to Q in minus Q out. So substituting the values of Q in and Q out, I am getting the answer. W net is equal to Cp T3 minus T2 minus Cv T4 minus T1. I hope you are understanding the points. You are writing down the equations in your notebooks. Let us proceed further with the next step. Now the air standard efficiency of the diesel cycle is given as eta diesel, that is equal to net work done divided by the heat supplied. So net work done divided by the heat supplied, that is Q in. Substituting the values of W net and Q in, I am getting the answer, that is Cp T3 minus T2 minus Cv T4 minus T1 divided by Cp T3 minus T2. Taking the common terms, cancelling the common terms, finally I am getting this equation, eta diesel is equal to 1 minus T4 minus T1 divided by gamma into T3 minus T2. Remember friends, when you take the common terms, you will be getting the answer 1 minus Cv T4 minus T1 divided by Cp T3 minus T2. Now we are knowing that Cp by Cv is equal to gamma. So Cv upon Cp is equal to 1 by gamma. So I have substituted that value of gamma in this equation. Is it clear to all the students up till equation A? Have you understood up till this point? I want the responses from majority of the students if you are understanding the steps of the derivation. It is very easy to understand. Just remember the concept Cp T3 minus T2 minus Cv T4 minus T1 divided by Cp T3 minus T2. So when this is divided by this term, the complete term is cancelled out. So I am getting 1 minus Cv upon Cp T4 minus T1 divided by T3 minus T2. Now we are knowing that gamma is equal to Cp by Cv. But here I am having the ratio Cv upon Cp. So I can write down that is equal to Cv upon Cp is equal to 1 by gamma. So substituting the value of Cv by Cp, that is 1 by gamma. So that is divided by gamma into T3 minus T2. Is it clear to all the students now? Shall I proceed further with the equations or with the derivations? Okay, so let us proceed further. Now friends, remember the important step. Now what we will be doing in the notebook, just mention this point in the big writing, remember this step. Now we will be finding the value of T2, the value of T3 and the value of T4 in terms of T1. Because of this reason, I have highlighted these three temperatures. I am repeating the point once again. Now we will be calculating the values of T2, T3 and T4 in terms of T1. So let us proceed further in the derivation. Now the compression ratio is defined as small r is equal to Vc plus Vs divided by Vc, the same equation of the Otto cycle. Considering the PV diagram, according to the PV diagram, we are getting Vc plus Vs, that is equal to V1, that is total cylinder volume, divided by Vc, that is the clearance volume. And according to the PV diagram, Vc is equal to V2. So substituting these values in the above equation of compression ratio, I am getting small r is equal to V1 by V2. Now friends, that comes the another ratio which I had already explained to you in the processes in the PV diagram, that is the cut-off ratio. If you remember, the cut-off takes place during the process 2 to 3. So writing down the cut-off ratio, that is RC is equal to V3 by V2. In your textbook, the cut-off ratio will be presented by the symbol, that is rho. Rho will be written in the cut-off ratio. But for my understanding, for making it simple, I am using the notation that is RC. So wherever in the book you are finding rho, I will be using that term, that is RC, that is the cut-off ratio. Is it clear to all the students? This is the difference between your textbook and my notations, my procedure. Is it clear to all? The notation about the cut-off ratio. In your book, the cut-off ratio will be represented as rho. In my discussion, I am using it as RC. Is it clear to all? I want your responses in the chat box. Okay, fine. So let us proceed further. Now calculating the expansion ratio. So expansion ratio we have already studied, that is equal to V4 by V3. Now understood the steps. V4 divided by V2 divided by V3 divided by V2. The answer remains the same. I am dividing V2 on top side and also the same V2 on the bottom side. So that is V4 by V2 divided by V3 by V2. Now from the PV diagram we are observing that V1 is equal to V4. So I am substituting the value of V4 by V1. So I am getting the answer V1 by V2 divided by V3 by V2. Now we have already done the analysis and found out that small r is equal to V1 by V2. So that is V1 by V2 is equal to R, and V3 by V2, that is the cutoff ratio, that is RC. So finally in the diesel cycle for the expansion ratio I am getting the answer V4 by V3, that is equal to R by RC. Is it clear, all the students? Have you understood these steps? In your textbook it will be written R divided by rho will be written. Is it clear to all? Are you understanding these steps? Very slowly I am proceeding in the derivation so that you are understanding these steps, you are remembering these steps, how we are getting the answers. Okay, thank you for the maximum responses. So now what we will be doing? Now we will be calculating the values of T2, T3 and T4 in terms of T1. And after getting these answers, we will be substituting the values of T2, T3 and T4 again in equation A. The T1 will be taken common from top and bottom side. So T1 will be cancelled and the remaining terms which are left, that will be our final answer. So let us proceed with the derivation. Now for the adiabatic isentropic compression process, that is process 1 to 2, I can write down T2 by T1 is equal to V1 by V2 raised to gamma minus 1. V1 by V2, that is compression ratio, that is equal to R raised to gamma minus 1. So I am getting the answer, that is T2 is equal to T1 into R raised to gamma minus 1. So our first target of finding the value of T2 in T1 is successful. Dear students, are you understanding the points? Are you noting down all the equations? Kindly share your responses in the chat box. If you are understanding these concepts, how I am getting all the answers. Okay, fine. So now let us proceed further. Now for the constant pressure process 2 to 3, we can write down the combined gas law P2V2 by T2 is equal to P3V3 by T3. But from the PV diagram, we are observing that P2 is equal to P3. So P2 and P3 gets cancelled out. So we are getting the answer, that is T3 is equal to T2 into V3 by V2. We have already got the answer of T2. Substituting this value of T2 in the equation for T3 and substituting the value of V3 by V2, that is RC. Doing the calculations, now I am getting the answer, that is T3 is equal to T1 R raised to gamma minus 1 into RC. So our second target of finding out the value of T3 in terms of T1 is again successful. Is it clear to all the students? Have you understood up till this point how we have calculated the value of T3 in terms of T1? Okay, fine. So now let us proceed further. Now considering again for reversible adiabatic expansion process, that is process 3 to 4, we are getting the answer T3 by T4 is equal to V4 by V3 raised to gamma minus 1. V4 by V3 is equal to R by RC. raised to gamma minus 1. So finally T4 is equal to T3 divided by R by RC raised to gamma minus 1. We are already having the value of T3. So substituting the value of T3 in this equation, substituting the value of T3 in the above equation of T4 and doing the mathematical calculations, we are getting the answer T4 is equal to T1 into RC raised to gamma. In your textbook, the value will be written T4 is equal to T1 rho raised to gamma. All the students, are you getting this answer of T4? Just you need to substitute the values, rearranging the terms, cancelling the common terms, the term which will be left, that is T1 RC raised to gamma. Or in your textbook, T4 that is equal to T1 rho raised to gamma. Have you understood all up till this point? How we have calculated the values of T2, T3 and T4 in terms of T1. I want the responses of the majority of the students if you have understood how we have calculated these answers, so that I can proceed further to the last step. Okay, thank you for the maximum responses. So now the last step of the derivation. Now the air standard efficiency of the diesel cycle. We have already written or find out this equation. Eta diesel is equal to 1 minus T4 minus T1 divided by gamma T3 minus T2. That is equation A. Now substituting the values of T2, T3 and T4 in above equation A. After substituting these values, after rearranging the terms, the final answer comes out for the diesel cycle, that is the air standard efficiency of the diesel cycle. Eta diesel is equal to 1 minus bracket 1 upon R raised to gamma minus 1 bracket complete into new bracket RC raised to gamma minus 1 divided by gamma into RC minus 1. Remember friends, in your book, the RC will be replaced by the notation that is rho. RC rho represents the cut-off ratio. I want the responses from the students if you have got this answer after substituting the values and after rearranging the terms. This is the final answer pattern which you need to get in the air standard efficiency of the diesel cycle. Very good. I am getting the maximum responses from the students in the chat box. I want the response from all the students that you are perfectly getting this answer. Very easy, just substitute the values in equation A, rearrange the terms and you will be getting the answer in this particular format. So repeating the last equation, the air standard efficiency of the diesel cycle, eta diesel that is equal to 1 minus 1 upon R raised to gamma minus 1 into RC raised to gamma minus 1 divided by gamma into RC minus 1. Dear friends, you need to remember this final equation because this equation we are going to use while solving the numericals of the diesel cycle. So friends, from this equation now I can conclude that the air standard efficiency of the diesel cycle depends on the compression ratio as well as the cut-off ratio. If you understand the equation, The air standard efficiency of the diesel cycle depends on the compression ratio as well as the cut-off ratio. The value of gamma, that is always constant, that is 1.4. So friends, with this, I am concluding the session from my side about the discussion related to the diesel cycle. One of the most important question can be asked in your examination, the diesel cycle and the derivation for finding out the efficiency of the diesel cycle. In the next BME lecture, we will be solving the numericals of the diesel cycle. As we have solved the Otto cycle, in the same manner, we will be remembering the equations for the diesel cycle, and same procedure we will be following for solving the numericals of the diesel cycle. Now friends, I am having some few minutes left in the meeting. So if you are having any question from your side related to the current topics which were discussed, you can ask me in the chat box. Notations, you can use any of the notations because it is up to us how we are using the notations. Okay, I intentionally highlighted that value of RC because whenever you are referring the textbook, you will be observing rho. In the numericals also, you will be observing the rho. But if you are remembering the cutoff ratio, then you need to remember this notation throughout all the points related to the diesel cycle. You need to stick on the one standard notation you are using. Is it clear? The student has raised this question. Okay, thank you for the response. Any other question any student want to ask related to the topic? Dear students, let me inform you that the concepts of the Otto cycle and the diesel cycle we will be using, we will be understanding these concepts in details in the practical approach in the chapter of the internal combustion engines. And at this point, we have already understood that the petrol engines, they work on the Otto cycle, whereas the diesel engines, they work on the diesel cycle. If any student is having any question of the topics covered in today's session, you can ask me in the chat box. Okay, so let me ask you a simple question from my side. What is the value of the cut-off ratio? What is the value of the cut-off ratio? What is the equation for the cut-off ratio? Okay, I am getting some of the answers of the students. The right answer, that is V3 by V2. Remember friends, do not get confused. Cut-off ratio, that is V3 by V2. Okay, thank you all. So we will be meeting in the next lecture for solving the numericals of the diesel cycle. Have a nice day.